begin.
So we will be explaining lipids, and we have made 4 molecules. These are basic fatty acid monomers. This is glycerol, which is bonding for both the di part and the poly. And then we have another polyunsaturated. And this is a steroid, which is a completely separate part of lipids. The basic materials we used were munchkins for carbons, green things for hydrogens, and melted airheads for oxygens.
Okay, so what I made here were 2 fatty acid chains, and this one right here is a mono-unsaturated because of the 1 double bond it has, meaning that the hydrogens are not full on all the carbons. And this one is saturated, and this one is called butyric acid, and it's what's in vomit, which makes it smell like that. And this one is crotonic acid, and this is the hydrocarbon chain along with the carboxyl part of it, which makes it a fatty acid. And it's important to note that these are nonpolar in the phospholipids part.
Okay, so I made linoleic acid, which is, as Teresa earlier said, a polyunsaturated fatty acid. So as you can see, it has an interesting structure, which it curves around. The reason that it is a polyunsaturated fat is because it has 2 double bonds between the carbons. And it is also worth noting that this is a cis-trans fat. So the difference between cis and trans is that in cis, everything is nonpolar, because you can see these are carbon-hydrogen bonds. There's limited electronegativity. Some, but few, polyunsaturated lipids are trans, which means that they are polar. And this occurs when you take a cis-trans fat, polyunsaturated fat, and you undergo through, it undergoes hydrogenation. And in this way, it rearranges and becomes a different isomer in which polar bonds are formed. However, as I said, this one is a non-polar one. And at the tail, you can see we have a carbonyl group and a carboxyl group.
So again, like I said, I made steroids. An important part of steroids is that they have these rings, and then here you have a fatty acid chain. This one specifically is cholesterol, which is a very important steroid in the body, and it helps with the production of sex hormones like estrogen, progesterone, and testosterone.
So now that we have all the parts to make an actual functioning lipid, as Therese previously said, the glycerol acts as the entire backbone of the phospholipid. I made sure when I was designing it to make it extra long to take into account all of the huge fatty acids we have to account for. So we're going to make a triglyceride, and this occurs as per any normal organic molecule. It occurs with a dehydration reaction. So a hydroxyl group is removed from both of the fatty acids. We're going to have to do a little bit of movement here. And one of the hydrogens is removed from each of the hydroxyl groups lining the glycerol. After this occurs, this obviously attaches to make a chain. These are quite large molecules, we apologize. And this will all attach to form an extremely long chain. And this would just be the triglyceride. All right. So, however, the lipids, we wanted to also show so these are the extra water molecules. However, there's also different types of, we also like to discuss phospholipids. So the only difference between phospholipids and regular lipids, so the only difference is, of course, there's a phosphate group added instead of one of the fatty acid tails. So this fatty acid tail would be removed, and the group that originally held the hydroxyl group would be flipped around, so that all of the fatty acid tails are moving in one direction, and the phosphate group is attached. Attached right here. Now you might be wondering what this little pesky airhead is doing here. This pesky airhead represents yet another R group in this huge molecule. This R group is the extra nitrogenous chain that usually makes it polar. So phospholipids are a crucial structure of membranes, as this portion, the head, would face the outside towards any aqueous solution, and this would face inward to create a membrane. Now, although phospholipids have no real need to be broken down, if we were to remove this, Fats are often need to be broken down to be transferred back into energy to be used. So now all of the water molecules we had before would rejoin the molecule so that all of the fatty acids would separate. Can you guys help me out a little bit? Thank you. So this would be separated. This would be returned to the fatty acids. Yes. And the hydroxyl groups would be reattached to the glycerol. So overall, the 3 fatty acid tails, it is important to note, can be of any type of saturation. We use 3 different types just to make it simpler for us to illustrate all the different types of, this looks a little bit like a mess, but to illustrate all the different types of fatty acid tails. But it could range from 1 unsaturated to 1 polyunsaturated to 3 polyunsaturated, depending on the lipids use.